any troubles with that. But I've asked Robin to give a talk about challenges and issues arising with time series and specifically change points in the energy sector. A few of us who are in the room are working in the energy arena, and change point problems seem to be causing a bit of a headache in that arena. So I've asked Robin, who's a considerable amount of experience, to talk about that. Because this is the only way that Robin can hear us, is this microphone here. So when questions come about, we will try and do that. But can I ask that, unless there's a really burning issue, we don't do any questions during the talk itself. It'll just be simpler that way. Okay, Robin, over to you.
Thank you very much, Idris, for this introduction. And thanks a lot for inviting me. Really, I apologize for not being here with you today. And it was really, as I told Idris, my back hurts at the beginning of December because I did some fancy stuff with my children. And so now I'm recovering it, and it was difficult to take the decision to have this trip to England. So I hope you understand. And it's not good for me because I only give you the talk and I cannot, have the discussion with you after. So after my talk, feel free to ask questions, but also to send me email or to discuss on the phone. I'm really open to that and that was the initial reason for me to come here. So I'm talking to you as more as someone working in the energy sector than in statistics. I've looked at all the talks before, not all of them, but some of those, and I really feel that you're really specialist in statistics, and I'm more working in the field of energy, even if I had a PhD in statistics, but that was 5 years ago, and now I've been only working in energy. So in my center, we work on integration of renewable energy in the electricity mix. So we are really thinking about the problem that can happen in the future if we have a lot of wind power, solar power in the future. And for example, I'm working now on a project where we try to see how the electric system can behave hour by hour and on each node of the network if we have 100% of renewable energy in the mix. So that's the kind of question that I ask myself. So in this question come the problem of variability of wind power, also of solar power, but today I'm going to concentrate on the problem of variability of wind power, and that's a little bit different. And so here is now slide 2. I'm gonna here is the content of my talk. After a brief introduction on variability and predictability, but it will mostly be images for you to see what it is actually. And then I'll try to answer a definition problem, and then I'll try to give you what kind of forecasting option we've been working on in the past years. So I don't think you're going to learn about new statistical methods, but I'm pretty sure that you will learn about our problem in the energy sector, and this will give nice exchanges. So now slide 3. On this slide, you can see the variability of wind power. Actually, it's quite the kind of graph that people that don't want renewable energy show to people, because when you see this, you say, okay, it's never going to be possible to have a lot of wind power, but that's more subtle than that, because the variability is different if you see it from the point of view of wind farm, which is really located in space, or if you see a country or a continent, and here it's a wind farm, so there's a lot of variability. And so it's a few wind turbines. A wind farm is a few wind turbines located at the same place, and it's a year. So in slide 3, in slide 4, so you see the same at the same wind farm. You see a week of variability, of a week of production of this wind farm, and the variability is different. So it's also the pattern. It's really different as you see it. So it's quite kind of it depends on the scale you're looking at, which is not really surprising, because on slide 5 I talk about the origin of this variability, which is related to obviously to the wind. But but the relation is not that obvious, actually, because what you can see here is for a single wind turbine, the power output as a function of wind speed. Each dot is one measurement for 10 minutes. So there are lots of weird stuff on this graph, and we have explanation for that. But even if you remove the outliers, I would say, you still have this tube, which is really not perfect, and the relation between wind speed and wind power is not really perfect. And that's also the reason why we, when we do time series analysis, we're mostly working on wind power, not on wind. And also, wind has better properties because it's known, it's been studied a lot by statisticians in the past, and it has a distribution that can be bring to a Gaussian one, I think, maybe the square root of the wind or some wind speed. But here it's really more convenient to work with the wind power because of this graph. Okay. So on slide 6, I point an important issue about this viability in the future, and that's really something important because we are having now new kind of wind farms which are offshore. So I say now, but actually Danish people, they've built these wind farms 10 years ago, so and maybe 20 years ago also. But the good example is this wind farm in Denmark called Untitled, where you've 200 megawatts of wind power, and it's really concentrated in space. But and so the fact that it's offshore and the fact that it's concentrated, that brings something new in the kind of viability we have, because the fact that it's offshore implies that the wind changes rapidly, because there's the roughness of the ground and it's really small, and this allows rapid changes in the wind production. And the fact that the wind farm is concentrated implies that there's lower aggregation effect, so stronger viability pattern. So now in slide 7, you can see what it means. It means that before it was actually what you see here is it's the production of a real wind farm, which is offshore, so it's the black one. It's normalized to 1, and so the black one is the offshore wind farm, and the red one is an onshore wind farm, which is really close to the offshore wind farm. So you see there's a slight difference in time. It's maybe 50 kilometers from each other. So they're related, but the kind of viability that you have offshore now, it's really a strong and brutal variation of the production. So this really comes to your topic, because it's brutal changes, and these brutal changes are really challenging for the Danish electric system. So now, so this is only viability, and then, so slide 8, only viability, and now slide 9, I'm gonna talk about how this can cause problem in predictability. So I'm not going to get into much details about how we do wind power forecasting for the short term. But it's statistics mainly, and or other people would say it's meteorology mainly. So it's these two communities collaborating and to produce a forecast of the wind power for the few hours ahead. And what's important to know is that for the 6 first hours, measurement on site is really an important explanatory variable. Then when you want to forecast further, it's really the meteorological model that is important. You're not going to get, I mean, the atmosphere dynamics with statistical model and with only a measurement on site. So you all know this, I think. And what appears, so we also do quantile forecasts, and that's what you see here with different quantiles, prediction, which are presented as prediction intervals. And what's important here is that you see the kind of error we make when when we have these rapid change of production. And it's not offshore here, but that would be even worse offshore. So I'm going to call these variation ramps because this is how we call them. So it's abrupt change for you. It's a change point, or that's how the people from energy call this. That's ramp of production, and it's a ramp of production, and also because people, if you want to balance this ramp in the system, you need to switch on other production bin if it's going down, and you need to do it fast. And so the ramp rate also is something important here. Okay, so what is the problem you see here with the prediction is that it's wrong, and also the quantile, the prediction interval is wrong. It's wrong, but it's globally it's calibrated. I mean, the 50% prediction interval got really 50 points in it in average. But in this case, you have like 10 or 12 points which are below the 10% interval. I think it's the 10% interval. So it's globally calibrated, but for that kind of event, it's successful. It's really wrong for successive steps. So that's the problem. And it's really because the prediction interval, they're not thought as something where you put information on the correlation of errors. So it's only marginally calibrated. So now on slide 10, so it's just to illustrate what kind of consequences can have this variation. So I'm not going into details, but what you need to understand is that it's not like having a big average error. It's like if you have now, we are talking about 1 gigawatt wind farms offshore in Great Britain, for example, and if it's 1 gigawatt that you lose before you thought, before the timing you thought, before that, so then you need to balance this with a production mean that has 1 gigawatt. So that's really these kind of errors, even if it's not often, it costs a lot. So now slide 10, no, sorry, 11. Slide 11, you see, so these errors are called phase errors, and they have a clear methodological origin. It's not really, it's not statistics, or statistics could correct this, but it's really the origin of this is a shift errors in the forecast of the methodological system. And so there are two kind of options to handle this that we saw from the statistical point of view. The first one is to improve the uncertainty. As I showed you, the intervals are not really suitable for that kind of event. And so improve the uncertainty estimation for the long term. It's something methodology is not really done for. And also they're working on tools for that. But and the other kind of improvement is for the kind of a reason where you can beat methodology, which means below 5 hours or 3 hours ahead. So for that kind of a reason, I'll talk about it later. You can do things to handle that kind of event. So now it's slide 12. So before I talk about the forecasting option, there was a big, I'm going to talk about the definition of what is this event. You might think this is obvious, but for the community, this really was a problem, because when people started to talk about ramps, there was kind of a consensus of what was a ramp when we talked to each other, but when we start to implement algorithms to forecast them, then we had to have a mathematical definition of what is the variation and what is defined by. Is it just, so it's like 13? Is it a variation 13? And yeah, you can go forward in the 13th slide. So what is a ramp? Is it like something, is it like 60% of the variation of the nominal power in 4 hours, 30% in 3 hours, 80% in 10 hours? So it's here the strength and the temporal scale that defined the ramp was really a question. But also, even if you agreed on that, that was a problem how to compute the timing of the ramp, to say the ramp appeared at that time. And that's, so slide 14, there was a few definitions that came to people from energy. So that might sound funny for you, because it's really not the smartest thing we've seen in statistics, but it was finite difference and max min. So you see, this was really easy to explain also to people, because they thought about big variation, and that was the first kind of number they wanted to compute. But then, so slide 15, from as you all know from the signal processing literature and statistics, there are lots of literature on the topic, and so it's related to your field of research, and there what's important is that we have to make people understand that filtering the noise was something really important here. So we propose that kind of other definition using other derivative estimation filters. So, and it appears, so slide 16, maybe I hope you can see the animation. It appeared that we had to find some sort of compromise, which is quite classical in statistics, and here it was really the compromise between the reduction of the noise you have when you have large windows, and the limitation of interaction between neighboring elements. So I don't know if it's the kind of compromise also you have, you might tailor this later. That really was the starting point of the methodology. So slide 17. Then we get into which is we really followed the statistical the signal processing literature here. We did not invent anything. That was just we proposed other definition than the finite difference and the max-min difference, and there was plenty of it. I mean, there are thousands of it in the literature, obviously, and so I think the most interesting one are the definition that that can be multi-scale, that try to find the variation without focusing on a given temporal scale. So this was given by, for example, the Lindbergh approach, where you try to find. So you can go forward in slide 17. You see this. You shall see now this maxima lines, which are really classical in the signal processing literature, where we chain the local maxima of the filtered signal at different scale, from the lowest scale to the largest scale, or the other way. And it was in the Lindbergh criterion. It's really the maximum overall scale that gives you that tells you if there's a big variation or not. So, and last point of slide 17, there came to be a few papers more recently. So Berbao is not from the wind power literature, but Caligo is from the wind power literature, where people try not to take the max, but other kind of metrics on this set of filter signal at different scale. They did not take the max, but combine them another way with a product in DAO, and with a sum in Caligo. So what you see on the left with the yellow color, it's the filter signal you get with a combination, a linear combination of two scale, of the filter signal at two scale. So obviously there might be many other ways to combine, and at that point there started to be a lot of people discussing, okay, but what's the best definition? And we were only seeking for a definition, and at that point, the people from energy, they started to say, okay, that's really abstract nonsense, and we don't understand what you're doing, and we don't understand how you compare your results, and what's the good definition, and what's all these papers for, and what all this abstraction for. So, oh yeah, also, sorry, slide 18, I forgot about the choice of the threshold, which also can be, can lead to a lot of discussions, and you can have a threshold which can depend on the scale, depending on if you think there are more noise, or also the shape of the noise, and also the autocorrelation of the noise can affect what is the optimal threshold here. So, so here I'm not going to enter the problem of the threshold, and I really will say that the threshold is a parameter that can be defined by the user. The end user at the end might want to set this threshold. So I was saying that this was a problem because it was difficult to compare the approaches. So we followed what people did like 10 or 20 years ago in the signal processing literature, and what we proposed was...
is your mobile phone ringing?
No.
Oh. We had some distortion here, but it's cleared up now.
Yeah,
Can you just go... Can you rewind about 30 seconds?
Okay. So, are you on slide 18?
Yeah. Yeah.
Yeah. Okay. Yeah. So now let's switch to slide 19. And what I was saying is that we followed the kind of methodology that was taken 20 or 10 years ago by signal processing literature, and we build a ramp model, because if you have a model of what is a ramp, then you can simulate the ramp with the noise, and then you know where is the ramp because you build the model, and so you can kind of compare the different approaches. So I'm going to present you the kind of model we built, which is, so it's like 20. So what's really specific here to wind power, which can be different to the Heaviside function you got in the signal processing literature, is that the production is bounded between 0 and 100% of the nominal power, and when you're close to the nominal power, you have only variation down the nominal power. So that's something specific also. That could have been a good agreement in favor of the max-min, actually, because the max-min would have been measuring the difference with the places where we have where we switch from 0 to 100 and from 100 to 0 quite rapidly, which is not the case of filtering methods. So that's, no need to go in further description of the formula. You see everything in the figure. It's what is the ramp definition for us. It's that kind of pattern you see on the figure replicated. And the replication is important because, as I told you, sometimes it's the length, the times length between two ramps that will imply the choice of the good temporal scale for the filtering. So now, slide 21, there was this question about on the noise model, and we made empirical studies on real data, and we found that kind of noise model, which is truncated Gaussian. It seems to fit. There are lots of literature in the wind power community on what kind of noise term you can have, but here it's really, the noise is really also specific to the model we have. So we made something simple here, and it's quite in an equation with the model. And what's important is that the noise level is proportional to the power production level. So when you produce more, it's quite natural to have more variability in when you're producing something around 0. So slide 22. So there was another other kind of random parameter in this model, and that was the timing between two successive runs. So there are actually there are 4 timings, which are the timing for the flat piece at 0. Then it's when the second piece is when you move from 0 to 100. Then there's a flat piece again, the third piece at 100, and then you go back down to 0. That's the 4th piece. So you have 4 pieces, and then their length is important here. So we try to generate with this model. We try to generate with realistic parameter different kind of time series with different parameters. And what we did, so here you see the result for one kind of parameter, and it's not really. So here, maybe the A parameter, which is the strength of the RAM, it's not 100. So the variability you see when the production is high in this graph, I don't really like it. It's not really that similar to the variability you saw on the graph where you saw the production, real production of offshore wind farm. But it's really approaching some reality here. So now this allowed us, slide 23, to evaluate the different kind of definition we had from the literature. And so slide 24, you can see the results which are given with the Canis criteria. Maybe, I don't know if you know this, because these are maybe more from the signal processing literature. And there are 3, here we put 3 criteria. The first one is the localization. So it answers the question, are we getting right the timing of the run? Or are we just a little before, a little after? So what you hear is the localization is given as with a root mean square error in terms of timing estimation. Okay, so the other criteria is the number of maximum in the filter response. So it's something that if you've run, you should have one local maxima in the filter response. If you've oscillation can be a problem because if you reduce the threshold, then you can detect several runs, and where you've only one. So that's something that is bad. And so clearly the results are in favor of the kind of filter that are from the old filter from the signal processing literature, and the maximum filter is bad in here. So that really convinced people, I think, from avoiding the use of that kind of filter. And you see also the last criteria. If you go forward in the slide 25, the last criteria is the signal to noise ratio. And it's difficult to say which one is better between the difference of boxes and the derivative of a Gaussian here, and that was not really the big question, because what came out is that, so slide 26 is that mid-scale approaches here are really are better. I would say slightly better. So if you manage to convince the end users that it's worth going multi-scale, then you get a little bit better results in terms of, here the results are presented in terms of area under the rock curve. So it's the performance in terms of classification. Are we good when we forecast a ramp? Do we catch it rightly or not? So it came out that also what you see here is that multi-scale is better than just one scale, and here the one scale is chosen kind of optimally, but it's chosen once. and here the timing between rumps, these are random variables. So it's varying. So that's why even if you choose it optimally, if it's only one scale for all the signal, it's worse than having a neutral scale. And what came out also is that the procedure of Lindenberg is much better than the other metrics on the scales. So combining the scale by linear combination of products, it's not as good as taking the maximum in this case. So so now you can go. So that was the conclusion of this. So now I'm going to switch to slide number 28 and talk about. So this is the second part of my talk, and I'm going to talk about the forecasting option. Now that the definition of the rump is something we all agreed on, I know you could not talk, so that's good for me to say this. Then now I can switch to the forecasting problem. The forecasting option with slide 29. What we've tried to propose here for that kind of so to solve the problem we have with this confidence interval not being right for 10 successive horizon time was to produce that kind of temporal uncertainty. You see in this figure, it's clear that if you can identify an event such as this big variation, if you can identify the timing of this event, it's possible then to say, am I right with the timing I'm forecasting, and what kind of errors I am making with my forecast. So then it's quite straightforward to have this timing uncertainty forecast. So that's what we've been producing. So I'm going to explain you how we produce this. So we're using, we're just making a regression. So for a given interval, we're trying to estimate the probability to have a ramp in this interval. So it's quite standard uncertainty estimation, and we make it with regression. And the novelty here was to use a product from methodology which is called ensembles. I don't know if you've heard about ensembles, but to make it quick, it's scenarios that are built by a methodological model. So you all know scenario, time trajectories for the same future, and the interesting point is that the methodologies, they obtain this scenario by making perturbation of the initial condition of the methodological model, and they throw the perturbations to the model, and what the result is a few trajectories of the future. The problem is that it's only a few, actually. It's only 60 trajectories in Europe. It's done by ECNWF, close to your place, in Reading. And the problem with this ensemble, I would say, is it's not really to be taken as independently distributed time trajectories, not at all, because it's 60 points in a space of dimension 10 at the power of 7. So that must make you laugh as a statistician, I guess. And so we choose to use them as explanatory variable to forecast the probability to have a ramp, and that's just by next slide. Just by trying to forecast ramp with each of the ensemble number. So what you see on the left figure is the forecast of the wind power for a given, at a given time for the next 72 hours, and so the red and the black lines are the forecast, and the observation is the blue line with blue dots. And each forecast is obtained with a usual forecasting model, taking one of the ensemble as input. So you've fixed 60 forecasts, so you can filter this 60 forecast with the improved definition of the ramp I gave you in the preceding section, and obtain so you can obtain a timing if you're for each member. Say this member forecast the ramp at this time, but if you take the local maxima of the filtered signal. But if here we took something that was we took the interval in which the filtered signal exceeds the threshold. So that's something different. So for each ensemble member, you end up not with a timing, but with an interval on which you're thinking that it might be a ramp. Okay. So when you mix all these intervals, you can build the kind of figure we have on the right here, which gives you the number of overlapping supports. It's quite difficult to explain what it is. So these intervals, when you have two ensemble member that forecast the ramp, then the supports overlap. And if you have 10 ensemble member forecasting a ramp at the given time, then you might think that the probability to really have the ramp at this time is higher. So that was the idea here. So I'm going to skip slide 31 and go straight to slide 32. And the way we did this was just to use classical regression techniques here with the kernel regression first. And so the explanatory variable here is the number of ensemble members predicting the ramp, and what we're trying to estimate, the regression function, is the conditional probability. Okay, and the other, in this kernel regression, we used variable width windows because there are few events where lots of ensemble members all predict the ramp. So it's the case where you have 40 members predicting the ramp is really rare. So you have a few observations on that side, and you have a lot of observation where only one or two ensemble members predict the ramp. So that's the reason why we had this window parameter chosen with the nearest neighbor procedure. The other procedure was the logistic regression. Slide 33, you can see the kind of result we obtained, and that was also an issue how to measure the quality of the event here. So on the left, it's quite classical performance measurement. It's what we call reliability. We just check that the forecast probabilities correspond to observed frequencies. So, and that's the case. And the interval you see is a confidence interval of what kind of variation we could have if the forecast probability were the true one. But due to the lack of observation, the forecast of the observed frequency are varying between this value, the true value. And so here you see I would say it's calibrated, it's reliable. And on the right, it's what we call sharpness. What we've just shown is that if you can forecast these probabilities to have a ramp in an interval, you can forecast these without using the ensemble, so making something. So without this explanatory variable, which was the number of ensemble predicting a ramp. And so if you remove this variable, you have forecast probability that does not depend on this number of members, and so here you can see that the forecast probabilities are really dependent on the number of members, and they are increasing with the number of members. So this graph on the right should show you that it was useful to use this explanatory variable. So now going to slide 34, there are lots of further works for this that might come later for this and also for the definition problem. The first one is the operation strategy. So you might not be concerned with that, but the whole community was concerned a lot with that. It was quite pleasant to see this idea of temporal uncertainty, and people said, oh, good idea, nice. But now the question came, how do we use this? and it's not obvious how to use this, because you still have the variation which are high and low. So you still have the magnitude variations. So the idea for the use of this is really related to the way we handle the way we handle the electric system, and it can be understood with this simplified illustration here, where you have energy. Imagine you've on one side you have energy production, and so the cost here is proportional to what you install, a nuclear power plant or a gas power plant, a gas turbine, and it's proportional to the produced energy. Because when you produce energy with a nuclear power plant, then it costs you something. It's quite low actually compared to. But with gas, it costs you the production of energy is quite expensive. And then on the other end, you have something called pure capacity. So it's a real simplified vision of the electricity network. But with this pure capacity, it's only here to be available to handle errors and last-minute changes. Okay, so here it's what you pay for is the availability, not really the energy, because you're not using them that much. And the problem with the round events is that you need a huge amount of capacity here, and you need what you need is. If your wind farm is 1 gigawatt, you need 1 gigawatt of gas, for example. But that's really not the aim of renewable energy to have. When you build one wind farm, you need to build a gas turbine close to it. So that's really not the kind of future we want. Or some people do that. And here you can imagine the kind of the value that could have our temporal uncertainty forecast for that kind of simplified system by comparing the two cases. So in case one, you sell a day in advance all the energy, so the energy in the gray part, but also in the red one, and you so you sell all the energy you can, and you get the money from this energy, but you need to buy a lot of capacity to compensate the errors. And in case B, you say, okay, I'm only gonna sell guaranteed energy, and so the gray part, and I'm gonna keep the red one and not selling it, and if it finally comes, then I can just do some down regulation, which means I can produce less than expected. It's possible with your wind farm. You can control it and produce less. So in this case, you can say, okay, but then how are we going to produce energy in the red part? If this forecast is done 1 or 2 days in advance, it's going to be really easy with optimization of the other production means which can take more time to start to handle the red part than if it's done at the last minute. So that's the kind of operation strategy we want to work on now with this. So that's also going to give us a cost function, which is something we search, something you search as a statistician when you want to do forecasting. You want to know what's the cost function. It really depends on how you're going to use the forecast here. So now slide 35. Other further works are on position errors. So the idea is that these are not only in methodology. You don't have only these phase errors where things are coming later than expected. It's also possible that, for example, here you're forecasting that the low pressure system is going to go through Denmark, and finally it's going just a little bit below in Germany, and the result is that you've no wind in Denmark. That's not really a problem for the global equilibrium of the system, because you gotta have this wind in Germany anyway. And if you wind turbine there, so that's not the problem. The problem is that if for the operation. So it's at the last minute, if things changed in your track, you might be trapped. So the work with position error might be similar by doing not only temporal uncertainty, but also, let's say, spatial temporal uncertainty. So that might be something I've seen there has been a lot of presentation on abrupt changes in spatial data or in spatial temporal data, and I think this could fit here. So slide 36, you can see all the kind of errors we could work on. This one I call gap errors, where finally there's a gap, even if this was not forecasted. So the low pressure system can split into two parts and use the kind of gap you see here. Not clear for me how to undo this now. So now let's switch to the last kind of option we have for forecasting, which is in the shorter term. So this is really so the definition and the forecast of temporal uncertainty are I think now published in the Journal for Wind Energy. But this one on the spatial temporal modeling is more recent, so it's ongoing work. So my apologies if it's not really, if I don't have good results for now. So slide 38. So let me tell you more generally why we go through spatial temporal modeling, not only for ramps, but the reason is quite simple. Oh, maybe you think it's obvious that we need spatial temporal modeling, so I should first tell you why it's not. It's not because with meteorology and we have physicians working on modeling with the physical equation of the atmosphere what's going to be the future, and this is spatial temporal, this is non-linear, this is using all explanatory value we want. So that's really, that should be the best. But actually, for shorter horizon, it's not, because the updates of that kind of model, because it's big, you don't get it that often. It's for the European model, it's every 6 hours. For regional model in your country, it might be every 3 hours, but it's not a full run. They don't run the full model for every 3 hours. It's not possible. It's too long. And it can take, if you run the full model, it can take almost 1 hour, depending on the model. So you get, when you have something going to Denmark, and it's coming earlier than expected, for example, you have the round coming earlier than expected, you learn that it's arriving earlier after it came with the meteorological model sometimes, because it takes 1 hour to go to Denmark. So you see it, and then you learn by with Meteor that, oh, this came earlier. So also the last reason is that wind farms, the wind farm production data is really a good sensor of the situation of the atmosphere, and you have lots of those. For example, in Denmark, what you see on the figure is the measurement we had on the project. We had measurement on each polygon here. So each polygon is a set of wind turbines, and we had the measurement of the power every 15 minutes for 5 years. So in meteorology, you don't have measurement every 15 minutes. You have measurement every 1 hour or something like that. So it's really got better resolution, but it's not wind. It's wind power, as I told you. And meteorologists, they're never going to use this because there's too much risk that these data are going to break everything in their model. So they don't want outliers. So slide 39, what you see is the kind of, if you use these data to build a spatial temporal model, you can get really huge improvement. And what you see on the left is, it's not my children's drawing, it's improvement for each of the wind farm you saw in the preceding slide. So there are 200 locations where we improved the forecast by using spatial temporal information. What we did was really something simple here. It was just a linear model. it was a bit further than the linear model, because if you do a linear model, you have 200 explanatory variables, and you use a lag of prediction that makes thousands of variables, so you need to do some lasso things and sparse estimation. So that's what we did here, but anyway, the improvement was really the kind of improvement you obtain not by improving statistical method, but by improving the kind of input you use. And when you see 20% of improvement, that's something interesting for this kind of horizon. So there, we are still working on this to make it even better. And so we're going to work a lot now on the statistical method for this to gain 2% of improvement. So, but that was really the spatial temporal information that was important here. So slide 40, you see that's an animation showing that how this can be maybe applied to RAM. So that was the question we asked ourselves quite recently. Is it possible to improve the forecast of RAM for the shorter term? Can we say the probability to have a ramp in 1 hour for this wind farm, it's big, so be prepared. So that's a different question, and what you see is ramp occurrence. So that's a small phase where there was, so I don't remember which one is what, but I think blue is when it's down, so it's going down, the production is going down, and red points are when the production is going high. So, so you clearly see there's a propagation. So we get into this propagation quite naively, and we compared a reference model, which is just a logistic regression of the future probability, with a model which uses the filtered signal. We uses to forecast the ramp at a given place. It uses the filtered signal at all the places in the past. So we used a shift in space and a lag in time, which makes it a propagation term. And that's so in slide 41. You see the kind of model we had, but we're still working on it, and it's even to formulate, it's not easy for now, so I'm not really happy with this. But what we used is, and it's we tried to make it robust by not using all the neighborhood, the moving neighborhood, propagated neighborhood, but we used the quantile, which is here the third quantile of the filtered signal, to say, okay, it's not when there are, there might be locally really big ramps that are not going to propagate, but when the third quantile is quite big in terms of filtered signal, and when it's propagating, then the probability to have a ramp in the future is high. So it's just it's one-sided because it's the third quantile, and so what you can see on the figure here, it's the kind of improvement you have with in terms of area under the curve, and also we used another score, previous score, and so I'm not. It's as a function of the velocity. So what I said is that there's a propagating term, and we choose to make it at a constant speed, and we estimated the errors as a function of the speed. And my idea was that there was going to be one speed, but clearly it's not the case, because you see the error. It's not really the improvement. Sorry, it's not really better for one given wind speed. One given speed, propagation speed. So there might be lots of ideas then to have adaptive propagation speed estimation, and how to make it depend on the wind direction, and so these are other further work. And the idea of propagation we've been working on a lot also for the other linear modeling, trying to make the coefficient depend on the propagation term. It's something we're working on now. So now let me conclude slide 42. So we proposed a framework to compare and discuss the definition of ROMs And this was really in line with older signal processing literature. So it's really, we're really thanking them for doing this. And this was the opportunity to put together different methods from the literature, defining ramps, and to bring agreement to the discussion, to bring consensus. So further research will include definition of ramp with a spatial temporal viewpoint, I think. So then we proposed a method to forecast temporal uncertainty, and I think the further research here is more on the decision process, how to include this in the decision process. And finally, we showed how spatial temporal modeling can improve ramp forecast in the very short term, and it's clear that in this direction there are plenty of work to be done. And, in the direction of spatial temporal modeling also, I really think that in the future there's going to be more interaction between meteorologists and statisticians. It's always the case. There are lots of statisticians that have worked in doing spatial temporal modeling that include physical equations, but I'm sure that in the future it's going to, and also meteorologists are working in the direction of statisticians because they're working a lot on what they call fast assimilation models. So they try to have a model that runs really fast and that does not solve all the equation. And so these two are, I think, going to meet each other now. They are meeting each other. But there's lots of interesting things coming up here. Thank you.
Thank you. Right, now you have to be patient with us while we work out how to pass this microphone around efficiently.
Yeah.
Time for any comments or questions? Chris.
Do I come to the microphone, or does the microphone come to me?
Well, it can come to you, maybe it can reside in the middle.
Okay, can you hear me?
Yeah, very well.
Very good. Chris Dent from Durham University, and I'm a fairly mathematical power systems person. Do you know of any actual control rooms which are using anything like these kinds of methods or other higher statistical technologies for integrating consideration of wind forecast errors into system operation? So, for instance, I know that National Grid in Britain, they contract probabilistic forecasts for individual sites, but that alone, without having some idea of the correlations between forecast errors, that doesn't allow you to look at the aggregate forecasts. I also don't think they have kind of treatment of the forecasts in when as well as the forecasts in what that you are looking at. Do you know of any other examples of system operators contracting these kinds of things?
So clearly, the time uncertainty, no organization are using it. It's clear, and it's really new, and it's really at the research level also for how to handle the forecast. If the question is about even the confidence interval I showed at the beginning, even those ones are not really used by the operators, and there are only few of those that are using that kind of interval, but still they're used by, for example, in France, there's not much wind power, but they use that kind of interval for demand forecast, and they use it not with. So we as statisticians, you often ask for the cost function, but they don't have that kind of cost function. They use it as a hint. They have the forecast and they have the uncertainty forecast, and they try to use it as a hint, but really not as in a quantitative way. The other two operators, I've never been to National Grid, but I'd like to. But I've been quite a lot to the Irish, to Sony, the Irish Northern Ireland electric system operator, and they're using, actually we are making a software which is called Anemos to forecast wind power, and we are providing them the uncertainty. We've been providing the uncertainty quite recently. Again, it's just a hint. And we've been discussing quite a lot with Energinet, and a lot of test cases here come from Energinet, which is the Danish operator. And Energinet is not really using probabilistic or confidence interval forecast. And when you see how they operate the system, they actually try to interpolate linearly the points for the future, and they really use methods that are simple, I would say, and the reason, so we told them, we showed in this paper that it's possible to make huge economy by using that kind of forecast and this methodology for operation, but we all have to understand that what they handle is the electric system, and it's what they deal with is the security of providing electricity, and they don't want to take too much risk with this, and so they are moving really slowly, and that's quite normal. So if you hear about other places where they use probabilistic confidence interval forecast in a quantitative way, I'd like to hear about this.
Yeah, I'll perhaps send you an email later, because there are all kinds of things you mentioned that I'm generally interested in. Also, National Grid do have some very good, at least one or two very good statisticians. I don't know if they're currently working on this, but they might be interesting contacts.
Okay, thanks.
Anybody else?
You can hear me, yes?
Yeah, I can hear you, but I can't see you. I'm trying to move my head, but thank you.
Okay. Clearly, one factor in failing to accurately forecast power production is the imprecision in the meteorological forecast. And that can vary according to whether the current weather system is of a stable type or of an unstable type. I was wondering if you have perhaps a simple statement about how much, depending upon conditions, of the prediction error can be attributed to meteorological prediction error.
Maybe can you put the slide number number 9? So I think I was. So this slide number 9 is hiding a huge literature, actually, because
Yes.
I did not say anything here, and I did not told you what actually we're using in the numerical weather forecast. And it's so from what I hear from you is that it's not really, it might be insufficient if you want to forecast the future uncertainty to use only the wind speed forecast, because in some meteorological situation, the variability might be higher than in other situations. The kind of non-stationarity you have on the wind, and actually we're in that kind of method. We're using other explanatory variable than only wind forecast, and so it depends. So I'm not going to tell you how we obtained this one in this figure, but there are lots of different paper and researchers that have tried different kind of variable, and it's clear that using variable that we can help you to characterize what is the kind of variability or the kind of chaos that is in the meteorological system at the given time. It's an interesting parameter, input parameter. So that was your intuition, I guess. And so you're right. You're totally right. And so I think there are lots of paper dealing with it, but there's not a real consensus on what is this good variable. There are plenty of ways to characterize the behavior, the behavior of the system, and I think I've seen two families of methods here. And the first family are using local forecast, for example, of temperature gradient or something like that, which gives you can help you to have a hint on the turbulence, but there are also other methods that are trying to observe the global pattern at a larger spatial scale. And what they do is they call it empirical orthogonal function, and it's actually a principal continuous analysis where they try to project the big situation, meteorological situation, into the first two principal components, and to characterize the global meteorological situation, and they use this as input. And they show in some cases that you have improvements here and not there, and so on. So then you come in the details and the devils that is with it. so it answers your question, but you're
more or less. On specific follow-up, there was a later graph where you showed the prediction versus the observation of, I think, the wind or the meteorological condition. And
it's on slide 33. And so this was, so is it slide 33 you're talking about?
It was earlier one than that, but anyway, you could use the observed meteorological condition as if it had been the predicted one, and then compare what you get from the observed one with what you got from the predicted one.
Mm.
I mean, I think there's some measure of quantification of the error due to meteorological prediction is what I was really aiming at.
Mm. Okay, so you would like to know in my final error what comes from meteorology and what comes from statistics,
yes,
which could be obtained by, comparing the, so in average, I don't have this, it depends also on the scale of the wind farm, and I've seen, I think I've seen a paper on this, but it's, so it seems that the error comes, I think I have a problem with this, because the way you normalize the error with the, if you're in the space of wind speed, for example, you will have an error on the wind speed forecast. So you will say this error is, 20% in root of, you have to, I mean, it cannot be an absolute value. It will be 20% compared to the average value of wind, let's say, to have an error in terms of root mean square, which will be in meter per second. And you will have an error in the wind power forecast, which will be in percentage of wind power. And how you compare this, you can put the error to the power curve, but then so I think I was not convinced by I like your idea, but I don't really see how we're going to fix this. The fact that these are not in the same spaces, and by going from one space to the other, you're kind of making the forecast, the remaining state of the forecast. But, so if you have any suggestion on this?
Well, I think what I was saying was, take the observed wind and predict the power from that using your relationships. take the previously predicted wind and predict the power from that, you now have two predicted powers.
Okay,
you can compare them.
I see. Okay, so actually we did something like that, because what we did, when I told you at some point that these phase error had their origin only on meteorology. So I remember I said this now. And we had the reason to say this. A precise reason is that we've tried, we have done some kind of benchmarking of statistical methods in a project called Animus that was like 10 years ago. And we, so there was 10 different statistical algorithms coming to make the forecast. And for that kind of event, all the forecasts made exactly the same error. Although they had different kind of error levels, in average, for that kind of event, they were really similar. And when you change the methodological model used as input from that, for that kind of error, it was also, you also got the same error. It means that statistical model were not changing anything in the errors, and changing the meteorological model was also most of the time not really correcting anything, because that was, so I don't know what you know about meteorological model, but in Europe, most of the meteorological models are using the same global input, which is ECMWF. So if ECMWF is pointing something wrong, then everything is going to be wrong for anyone.
Okay. So I think we'll wrap up the discussion there. Robin, thank you very much for doing this talk. It must be quite surreal doing it to an audience on the screen like this. So thank you very much for doing a great job of that.
So thank you very much. So again, feel free. I'll be happy to hear about questions and suggestions for further stuff. So I was here for that. So have a nice day and end of conference.
And unfortunately, I'm sorry about this next bit. So because we've got quite a few new faces here this week, we've got some wine and soft drinks outside now. So just make those meetings so everybody can get to know each other. Really sorry I can't have some whizzed across the internet to you there. So hopefully,
I think I have to switch off the camera now. Bye.
Thank you. Bye.